Okay, so we're going to talk about fire behavior of post-install anchoring systems. This is not a topic that falls directly under the scope of the manual practice, but it does provide a design, performance-based design method for these types of systems. So the background research was carried out at the Scientific and Technical Center for Building in France, and the design concept was developed with Pinoteau. So these post-install anchoring systems are basically bars that are glued inside concrete using a structural adhesive. Practically, what happens on the construction site is that for an existing concrete structure, a hole is drilled inside the structure. This hole is then cleaned by air blowing and brushing. A polymer adhesive is injected inside the hole, and then we insert the rebar. And typically, the curing of these polymer adhesive takes generally 24 hours. So at the end, we get a bond system, which is created of the concrete around it, the bar, and a polymer adhesive. And in the scope of evaluation and design, we generally separate the anchor application from the rebar application. In the case of post-install rebars, these can replace, in some cases, the traditional cast-in rebars, where there is no polymer adhesive. And the fire design of cast-in rebars is covered by the International Building Code, which gives a minimum concrete covers in order to protect the rebar from the fire. So these prescriptive concrete covers depend on the fire rating we're looking for, the type of element, and also the type of concrete. In the case of post-install rebar, we have a polymer adhesive around the bar, and this makes them much more vulnerable to high temperature. And that's why there was a need to develop a design concept that was associated to this type of technology. So a method was established about 10 years ago and is today used in Europe for design and evaluation of post-install rebars. The method has three main steps that we see here. In the first step, we carry out a thermal calculation inside the structure in order to know at each time what is the thermal distribution along the rebar. And this can be done either by chart reading or by numerical simulation. In the second step, we establish a relationship between bond strength and temperature, and I'll come back to this later. This is a product-dependent relationship. It depends on the mortar that we're using. And finally, in the last step, knowing the temperatures and this relationship, we can associate a given bond strength to each segment along the bond, and then integrate along the entire length in order to get the load bearing capacity at a given time during the fire. And this load bearing capacity is then compared to the demand, to the applied load, in order to know if collapse occurs or not. So in the next parts of this presentation, we're going to start by presenting how we achieve this curve, the second step, which is basically product evaluation. Then we'll present the method that is used and how we validated this method with full-scale tests, and then we'll finish up with the design concept. So product evaluation is acquired by doing tests. These tests are done on small concrete cylinders, which are about 10 inches of height. We bond a rebar inside the cylinder, and we position two thermocouples along the bond in order to measure temperature directly along the bond line. The sample is then taken and put inside an electric oven, and the bar is connected to a hydraulic jack, which applies a constant load all throughout the heating. So we heat up the sample, and at a given temperature, failure occurs. So for a given load or stress, we can associate a given temperature. And by repeating these tests several times with different load levels, we obtain different temperatures, and we can plot the bond strength versus temperature relationship. So we provided guidance and put rules on this curve on what was the spacing between the points and what type of analytical function should be used in order to describe the behavior of a given product. And this curve is used as entry data for design. Basically, we add up the contribution along the bond of each segment, which has a different temperature, after having calculated the temperature distribution along a bond in a building exposed to fire. And so this is what we call the resistance integration method. And we validated this method using full-scale testing. The philosophy of this full-scale testing is we have a full-scale structure. We predict when failure occurs using the resistance integration method, and then we compare this to the experimental observation. So we did two full-scale tests. The first one was on a structure which was a wall cantilever beam, which was connected to a wall using post-install rebar. So here, the bonded part of the rebar is only inside the wall, not inside the beam. There were two beams in order to check repeatability. We took the tested structure and put it on top of a furnace where we applied an isofire up until collapse. And we measured the collapse. The first beam collapsed after 178 minutes, and the second beam collapsed 16 minutes later, which suggests relatively good repeatability. And this is in good accordance with the calculated model, which predicts a failure between 2.5 hours and 3 hours. And at the end of the test, after cooling, we did check that the failure was indeed due to the slip of the rebar in the adhesively bonded spot. So that was the first test. The second test was done a few years later and was on a structure which was a slab connected to a wall using 8 post-install rebars. And the goal of this test was to see if there was stress redistribution between the rebars during collapse. And here again, there's a good accordance between the calculated predicted failure time and the observed time. We had collapse after 118 minutes, and the predicted failure time was around 2 hours. So both of these tests have been published in the Journal of Engineering Structures, in addition to other validation tests. So this allowed us to validate the resistance integration method, which was the first step before determining a design concept.
So then the next step here is to translate this into American design, where we have development lengths as the basis for our reinforcing bar design. So what we see here is just a modification of the development length, but needed for fire conditions. So on the left side of the equation, we just get the bar yield, which is the thesis of development length design. In the middle here, we have pi d tau equivalent, which is basically the effective bond strength of associated with the cold development length. And then the integral part here that you see is saying, how do we modify the development length along the bond stress along the length, or how do we take the individual contributions of the fire, of the capacity of the adhesive under fire conditions over the length. So this can be expressed as an integral or as a summation. Okay, and this is showing that the tau equivalent in this equation is based on the cold development length. So the steps to actually do this in the US would be first to determine the cold development length using ACI 318. Then to use that development length to come up with an equivalent bond stress along the entire length of the bar. Determine your temperature profile for whatever your fire load is, whether it's prescriptive based on the time or performance-based design. And then, of course, using your geometry as an input. Then what I think will be the most common way to do this would be to discretize that length and come up with the individual contributions of bond along the length of the bar, and then add lengths until you reach the yield strength of the bar. So we have a couple of different cases. The most simple case would be if we have uniform temperature along the length of the bar, in which case you would have also a uniform reduction in the bond strength due to that temperature along the length. So then the calculation based on the development length, you can come up with an equivalent bond stress and have a relatively straightforward solution to how much longer your length needs to be based on the reduction of strength along the bar. The more complex or general case would be where we have a temperature distribution along the bar, in which case you have to discretize and add up the contributions and add up more and more lengths until you reach a development length that yields the bar. And so here we're seeing just a tabulated format. Each line in the table is a new length of the bar until we reach development length, until we reach yield. So now the next step also is going to be how we deal with the topic of anchorage, anchors that are directly exposed to fire. So the differences here are that we have that exposure where the steel is actually experiencing the fire itself potentially. We have shorter embedment depths, and in the anchoring philosophy, different failure modes. And so all of those would have to be considered when we're talking about these anchors under fire conditions, as opposed to post-installed reinforcing bars. So basically, in conclusion, what we have now is a reliable solution for post-installed reinforcing bars that we've shared based on the product specific evaluation and the temperature fields along the bar. And we have a proposal for this, and we would like to address the topic of anchors that is more complex in future work. So that's it.
I have a question. Does the stiffness of the adhesive also change with temperature, or just the strength? And it appears that it's implicit in the method that the stiffness is uniform along the whole length. Does that matter?
The question is, does the stiffness of the adhesive also change?
Yeah. Right. So I had a slide or two to answer this question, but I'll do it orally. So the stiffness does change a lot, especially when we pass the glass transition temperature. We have a drop by almost 2 orders of magnitude of the modulus of shear modulus. Now, the fact that the stiffness decays is actually beneficial in redistributing the stress, because it's true that in this method, the resistance integration method, we only talk about stress without looking at compatibility between displacements. And the fact that we become less stiff allows the stress to redistribute and go get the cooler areas behind at the end of the bond, which are the mechanically most resistant. So the calculated development lengths seem achievable for slab cantilever slab connection, but how does it satisfy length requirements for wall slab and external beam column connections? So basically, the only place where structural configuration comes into play in this method is with the thermal profile. We don't look at the demand. The demand on the bar is not explicitly expressed. It's just linked to the yielding of the bar. And so depending on which type of structural configuration we are in, we're going to have a thermal profile which will be different. Of course, if we have a connection between a slab and a wall, we're going to have a gradient. If the fire exposure is parallel to the bar, we're going to have a uniform temperature along the bar.
Eamon Connolly from Chicago, McHugh Construction. Great presentation, really topical. In Chicago, we do concrete cores, and we've had a history of doing drill and epoxy. Our city officials have had expressed a concern on this issue, and I know I've spoken to some of your colleagues in the past about this, and this research is great. And I know that you guys have published literature on this topic, but what you were showing there was like required embedment depth of like 30 inches. So that becomes like, I guess that's what I was reading, that becomes a kind of a difficult a thing to achieve in the field realistically. Is that 30 inches basically correct roughly?
Yeah, so if we're modifying the development length, the development length would be the starting point. So we will not allow lengths shorter than the development length in that particular framework.
Sure.
But if we now move into the topic of anchorage and looking at the other failure modes in anchorage, it's conceivable that we would have smaller embedments possible even for reinforcing bars under that paradigm. But that's something that's going to have to come in subsequent proposals.
Sure. Okay. Thanks.
Yep.
Great. Thank you both.